a cell. On one side, this is the membrane going down the middle here. On one side of that membrane, we've got a lot of solute, a high solute concentration. On the other, a much lower solute concentration. And they give us some numbers here. They tell us that over there on the side A, that our solute potential, remember that psi S, that's the solute potential, is -1, and the pressure potential, 0. You guys ought to know to get water potential, what do you have to do to those two numbers? Add them up. Solute potential plus pressure potential equals water potential. So over here, the total water potential, -1 plus 0, just -1, right? -1. Over here, -2 plus 0, or -0.2, -0.2. Important point. Which way does water move in terms of water potential? High to low. So in this case, which way does the water go? From higher to lower. So it's going to go from B toward A. So your first answer would look like that. Okay? B to A. Higher water potential to lower water potential. Now, if the solute could move, maybe it can't, but if the solute can move, which way is the solute going to go? Higher to lower, right? It's going to go this way. It's going to go to the right. Let's scroll down a little bit here. All right, the next question says, which side is hypertonic? And that would be side A. Hypertonic means more what? More solutes, higher solute concentration. So this would be side A. And then hypotonic means less solutes, and that would be side B. You guys with me on that? All right, let's scroll down to the other part. So same basic scenario here, but this time we've got an added variable. This time we're applying pressure. Now, to give you an analogy, let's think of this pressure plunger like a syringe. If I decided that Janelle needed a flu vaccination, and I'm going to give Janelle a flu vaccine, and here's my syringe. First of all, I'm going to have a bottle that has flu vaccine in it, right? And I'm going to take my syringe and do what with it? Go into the bottle, and then I'm going to do what with that? I'm going to pull up the plunger, right? When I pull up that plunger, what am I creating inside my syringe? What kind of pressure? If I'm pulling away from the liquid, what kind of pressure am I creating in there? It's called a negative pressure. Because basically what I'm creating there is almost like a vacuum, right? And how does pressure always push things? Pressure always moves things from where to where? Higher pressure to lower pressure. So where's the higher pressure in my analogy? If I have a bottle of flu vaccine and I pull up on my plunger, where's the higher pressure? In the bottle, and the lower pressure is in the syringe, so the flu vaccine gets pushed into the syringe. Pressure never sucks. Pressure always pushes. And it always pushes from what to what? High to low. What I'm saying though, in this particular picture, what it's trying to show you is that we're taking the plunger and we're pushing it that way. That's the opposite of what I just described, right? Once I get my syringe loaded, I'm going to go up to Janelle, and I'm going to push in on the plunger, right? Creating what inside the syringe? Lots of pressure. We call that a positive pressure, because the pressure in my syringe is going to be higher than the pressure where? In her arm. And which way is that liquid going to go? Higher to lower. It's going to go in. So positive pressure is when you're pushing inward on something, like we're doing in this example. Negative pressure would be if we pulled the plunger backward like that. And when we pulled it backward, that's basically creating like a vacuum over here, correct? And that's what we call a negative pressure. Does that make sense? So this is positive pressure. We're pushing in on the plunger. We're creating pressure. That's positive pressure. Negative pressure is when you pull the other way, and you're basically creating like a vacuum effect. Here, though, same thing to begin with. We want to calculate the water potential, and we know that water potential is solute potential plus pressure potential. They're using this T just to mean what? Total water potential. So over here, it'd be negative 0.8. And over here, it would be what? 1.8, positive 1.8. So which way is the water going to move? High to low. So the water is going to move that way, B to A. It doesn't ask us about the solute here. We have positive pressure. Which side's hypertonic? A. B is hypotonic. Makes sense? Well, we will, eventually. All right, the next part. Let's get out that other handout now and take a look at it. I'm just going to kind of go through this one with you. This is something that in the past I never taught because I never thought it was something that they would ever ask you on the AP exam. And then a couple of years ago, they asked it. And now I think it's more likely that they'll ask this kind of thing because there's a whole set of math questions. And there's only a few things they can ask math questions about in biology, at least the biology we're doing. So what we're looking at up here is an equation to calculate just the solute potential. Just an equation for this part of water potential.
Teacher, please for an interruption. Any sophomore or junior that would like to place an order for a class ring, please go to the cafeteria at this time. Thank you.
All right, so the equation for solute potential is negative I CRT. That should be a capital C. It looks kind of like the lowercase, but capital. Now I want to talk about each part of this. You need to know this equation. You need to know how to find each part of it. Let's first of all talk about the I part. As you can see on this handout, the I stands for ionization constant. Now again, if you're not very good at chemistry, you need to be listening. Basically, for this kind of thing, we're going to be dealing with two kinds of chemicals, sugars or salts. What kinds of bonds hold sugars together? Let's back up a step. What three elements make up sugars? Carbon, hydrogen, and oxygen, right? C6H12O6, that's glucose. Those are all what kind of elements? Carbon, hydrogen, and oxygen. What do they have in common? They're all 9 metals, right? Carbon, hydrogen, oxygen, all 9 metals. What kinds of bonds form between 9 metal atoms? Covalent. Share electrons, right? If you put a sugar in water, does it turn into ions in the water? No, it just dissolves. It does not ionize. So point number 1, the ionization constant for a sugar is 1. For anything that's covalent, like a sugar, and in these examples, it's going to be sugars, it might be glucose, it might be sucrose. For any sugar, the ionization constant is just going to be 1. But salts are a little different. What is a salt? By definition, what is a salt? It's a metal connected to a nonmetal. By what kind of bond? Ionic. When you put ionic things in water, what happens to those ionic things? What's the word for what happens when you put an ionic compound in water? Well, no, that's not what I'm looking for. They disassociate. They turn into ions, right? When an ionic compound dissolves, it breaks up into its separate ions.
What about the condensation synthesis?
Different thing altogether. Let's look at the most basic salt that we deal with, sodium chloride, right? Table salt. if we put sodium chloride in water, 1 formula unit of sodium chloride is going to break up into what ions when we put it in water? All right, sodium is what charge ion? Na plus, and chloride is Cl minus, right? Now, how do you come up with those charges? How do you know it's Na plus 1 and Cl minus 1? You look at periodic table. Sodium is in column number 1, right? Which means it has what? 1 valence electron. It's trying to get to what magic number of valence electrons? 8. It's a metal. What do metals tend to do with their electrons to get to 8? Do they give them away or take them? They give them away. Well, it only has 1 to give away, and then it drops down to that next level, which already has what in it? 8. So if it gives 1 negative away, what happens to it? If you give a negative away, you become positive, right? Chlorine, on the other hand, the halogens, group 7, they have 7 valence. Nonmetals do what to get to 8? They gain them. They take them from something else. So chlorine just needs to gain 1, right? So if you get an extra negative, you become what? Minus 1. You become minus 1 in this case. But here's the case. To find the ionization constant, first of all, you need to do this. Then you look, 1 formula unit of sodium chloride, 1 formula of NaCl gives you how many ions? 2. So what's the ionization constant? 2. The ionization constant for sodium chloride is 2. 1 formula unit of sodium chloride, when it dissolves into its ions, gives you 2 ions, 2 moles of ions. So the ionization constant for that is 2. For sodium chloride, let's be specific. For that particular salt. That's not the only salt, right? So let's do another salt. Let's do this salt. How do we know that's a salt? Because it's what? Combined with what? A metal and a nonmetal. So held together by ionic bonds. So to get the ionization constant, if that was our solute, first of all, we break it up. What ions is that going to break up into? Calcium. Calcium's in column 2, so it's going to be Ca plus 2, right? It's going to lose 2 electrons. Ca plus 2. And what's a fluorine ion? F minus 1, right? But how many of those F minus 1s do we get? 2 of them. So 1 formula unit of calcium fluoride gives you how many ions when it breaks up? 3. So what's the ionization constant for that? 3. Does that make sense? Let's do one more.
You have to break it up like that when you spaghetti.
I mean, once you get good at it, you can just break it up and then just do it in your head. But trying to show you where it comes from. Yeah, you could. Yeah. Here's aluminum bromide. Join me, ladies. Aluminum bromide. Aluminum, that's a salt. We know it's a salt because it's got a metal and a nonmetal. Aluminum is going to break up into what ion? Al plus 3 or 3 plus, whichever way you want to write it. I always like to write plus 3. But you'll see some chemistry teachers that like to write 3 plus. Same thing. And then this is going to break up into bromide ions. A bromide ion is Br minus 1. And this 3 down here, this subscript tells me I've got 3 of those, right? 3 bromide ions. So my ionization constant, 1 formula unit of aluminum bromide gives me 4 moles of ions in solution. So my ionization constant is 4. Does that make sense? Everybody can do that. So if it's a sugar, what do we say the ionization constant is? 1. If it's a salt, you have to do this. And you figure out how many ions do I get from 1 formula unit of that particular thing. Not too bad, right? Let's go a little further. So far, let me write this equation a little bit bigger up here. So we got our ionization constant. Big C. stands for concentration. Almost always, what do we measure concentration in chemistry? What unit? Molarity. That's what you need to use here. What does molarity actually measure? What does molarity measure? Moles of solute per liter of solution, total solution. Moles of solute per liter of solution. But this is molarity. This is typically going to be given to you in the problem. If you look down here, it tells you the molar concentration of sodium chloride in an open container is 0.3. I gave that to you. This R is also going to be given to you. It's called the pressure constant. You've seen a very related number before in chemistry when you dealt with which gas law? When did you have a number that looked like that in chemistry? Which gas law? Ideal gas law. PV equals nRT, right? It's called R. But that number, 0.0831, is always going to be R. Now, it's got some weird units on it. Keep up with those units. They're going to give you this number. This is not a number you need to memorize. They're going to give it to you. You just need to know how to use it. But look at the units. Liter bars divided by mole times kelvins. We'll deal with that in a minute. And then the T is the temperature. But it's the temperature in which unit? Kelvin. They're probably going to try to trip you up and give you the temperature in a way. Celsius. How do you go from Celsius to Kelvin? Yeah, 273. So let's look at how this problem would work. Calculate the total water potential for the following solution. The molar concentration of a sodium chloride solution in an open beaker has been determined to be 0.3. The pressure of the solution open to the air is 0. So the pressure part of the water potential, 0. We know that the total water potential is the solute potential, this, plus the pressure potential. They're telling us the pressure is 0. So the water potential is going to be whatever this is, the solute potential. So now we're going to use this equation and we're going to find the solute potential. Dealing with sodium chloride. It's salt, right? So what's the ionization constant for sodium chloride? 2, right? NaCl is going to break up into Na plus, Cl minus. One formula unit of NaCl gives us 2 moles of ions. Our ionization constant is 2. All right, the concentration, if we keep reading, is given to us 0.3. So we're going to write that down for C. Now to get my units straight, I'm not going to write big M. What am I going to write? What do we say big M means? Moles over liters. So I'm going to write moles over liters, so I keep my units straight. All right, we'll keep reading. We know the next thing we need in our equation is R. And R is this number that's going to be given to us. 0.0831. But let's get the units up here. It's liters times bars over moles times kelvins. And then the last thing we need is the temperature. And that's given to us in the problem. It tells us 27 degrees C. Just what Kelvin temperature? 27 C is 300 Kelvin. Add 273. Does it say what? I still didn't hear you. Liter, you talking about here? 0, it's just this copy there. All right, so let's check out our units. What happens to the kelvins up here? They cancel. What happens to the moles? Moles here, moles here. Liters here, liters here. All the units canceled out except what? Bars. Bars are a unit of pressure, basically. That's going to be a common unit we get for water potential. It's going to be in bars. So now we just do the math. Multiply that out. So we got -2 times 0.3 times 0.0831 times 300. So we get a solute potential of negative, if we round it off, it'd just be negative 15, negative 14.958. We're just going to round it to negative 15 bars. Now remember, they told us that the pressure potential was 0. So the total water potential inside the solution is negative 15, right? Negative 15 plus 0. Water potential is negative 15. Keep that in mind. What? That's how you do it. That's it. As hard as it gets. They told us the temperature was 27 Celsius. Add 273 to get Kelvin. All right, that's the first part of this problem. Now let's scroll down a little bit. And let's look at the second part. Oops. Here's the second part. Remember that we have a container. And the container has a water potential of negative 15 bars. What they're telling us in this problem is that now we have a red blood cell with an internal water potential of 12 bars, positive 12. We're going to put that into this solution. So we put our red blood cell in here. The water potential of the red blood cell is 12 bars. And we want to know what's going to happen. Before you mark one of these answers, I want to tell you that the people making these up have made several mistakes. And they made a mistake here too. Flip between A and B. Hypotonic should go here, and hypertonic should go here. So flip the hyper and hypotonics. And now pick out what the right answer is. Take a minute, look it over. We've got a red blood cell with a water potential of positive 12 bars. We've got a solution with a water potential of negative 15 bars. And we want to know what happens. So pick out an answer.
Not a negative 15.
Negative 15. So you guys tell me, what's the answer? Which one? It's B. Water always moves from higher water potential in here to lower water potential out here. And the reason it's moving, where are the solutes at? Where are most of the solutes? Outside. How do we know that? If we have a negative water potential, that means there's a lot of solutes. The bigger that number becomes negative, the higher the concentration of what? Yeah. The more negative the water potential becomes, the more solutes there are in that solution. So the water's going to move out. It's moving from higher water potential to lower water potential, from hypotonic to hypertonic, from less solute concentration to more solute concentration. And which one did I leave out? Higher concentration of water to lower concentration of water. That's water potential. There will be a question like that on the next quiz. There will be a question like that on the test. There will more than likely be a question like that on the AP exam. Know how to do it. I just recorded that little conversation we had there.